Welcome, this is lecture number 50. In this lecture, we are going to talk about large signal controller tuning in buck converter. What are the objective and then derivations. So, in this lecture, we are first going to recapitulate the PID controller tuning objectives, then large signal modeling of a buck converter, then large signal based tuning in a buck converter and the summary of tuning parameters. So, the time optimal load step recovery. First, let us try to understand, because we have discussed in the last week, like in the boundary control, like lecture number 47, that as well as the 48, what is the concept of time optimal control, in which if you start with one I think the load condition, suppose we are here, the load condition here, and now there is a load step transient, and this is my load step size of delta I0 step size, and it has to go to the next load current, right. And during steady state, it will have like a on off operation. This is like a on state and this is like a off state. Then when there is a load transient, it will go by this path and it will hit this surface, and in one switch action it has to come back. It has to come back, sorry, it has to come back again, this surface it will hit, and then it will again like continue like this and this. So, that means we will have this is our off state trajectory, on state trajectory. So, this is the sigma where, and we know all these sigma 1, sigma 2, which is the for used to generate the hysteresis band, they have just a only offset hysteresis band. Otherwise, sigma 1, sigma 2, sigma 3 all have same slope, because sigma we have if we discuss about sigma, this is a sigma, and where we have a current hysteresis band. So, sigma consists of error current gain into error voltage equal to 0, whereas if we want to consider the band hysteresis band, so sigma 1 will be sigma minus delta IH by 2 and sigma 2 will be sigma plus delta IH by 2, that is it. Now, if you rearrange sigma, that means we are multiplied with minus 1. So, it will look like a traditional error voltage, like error voltage where Vref minus V0 and reference current, and this will look, the complete will look like if you take this complete thing, it is like a peak current reference consisting of the reference current, which can be load current, plus the proportional gain into error voltage. So, it is like a proportional control with load current feed forward, and which is compared to the inductor current, that means this is a peak current. So, this can be translated, and if you put a hysteresis band that we have discussed sigma 1, which is just to this band is created delta H by 2 in either side, so that the overall band is delta H, and you have to choose delta H in such a way, so our steady state switching frequency will meet our desired switching frequency requirement, that is it. Okay. Now, another problem, you have to choose this proportional gain. How to choose that? Now, if you rearrange, if you link, if you recall our earlier concept, here this current, if we replace Iref, the reference current is equal to load current, then load current minus inductor current is minus capacitor current, and the minus capacitor current means we have C dV0 dt, right? Right. Now, what is our V0? We know that our error voltage is Vref minus V0. So, this can be written as, if Vref is constant, it can be written as minus of, that means if we take this one, minus of C dVe dt. Okay. So, this is exactly what minus, here is a minus sign, minus minus plus. So, this capacitor current expression we have given. Now, the sigma will be replaced by, so sigma we have, this is our error voltage. So, that means the sigma here we can see Kp into error voltage plus because this whole term is minus of C into dVe dt, right, C into dVe dt. Now, if we normalize, if we divide by C, then we will get small kp by C, which we are taking as a capital Kp. So, it will look like like a control voltage, the switching surface. So, it is like a, this looks like our control voltage, like a voltage mode control, is a PD controller. Proportional controller gain and the derivative gain is unity because we have normalized it. So, it is a PD control. Okay. Proportional gain and derivative control, proportional control. So, this part is our proportional, this is our proportional action, this part, and this part is our derivative action. Okay. Now, this sigma Kp into error voltage, if we add an integral term, that means we have an integral term into the integral of the error, right. So, what we will get? Then the whole thing will look like a PID controller. Okay, see a PID controller formulation. So, we can, in a buck converter, we can show that this actually represents like a PID controller, and this has been reported in this paper. How to formulate this? The next object. So, we have a PID controller. So, here since our derivative gain, it is normalized, so it is unity. So, we do not need to define or obtain any derivative gain. So, we have only 2 degree of like a 2 unknown variable, this and this, these are the 2 unknown. So, these are the unknown variable that you solve. Now, out of these 2, the proportional action which corresponds to this is very fast, because this primarily drive the switching action, the switching surface, and which will act during a large signal transient, right. Because it is so fast that during the large signal, this proportional gain is going to decide the shape of the trajectory. But integral action is used to remove the residual error, so that the output voltage will approach towards the reference voltage. So, this action will come during steady state or close to steady state, when the objective is to achieve almost 0 steady state error. But this has almost negligible impact in this large signal recovery, and where we want to achieve time optimal recovery, and there our primary role is to choose a suitable proportional gain which will achieve the one switching action. Okay. So, the proportional gain here we are using large signal model, because that is to design our trajectory switching surface in such a way we get one switching action, whereas the integral gain is used using, or it is designed using small signal model, because this will act during steady state and it has a very slow scale behavior near to steady state, so that it will try to eliminate the steady state error. So, let us first design how to design integral gain. So, if you recall in lecture number 34, if you recall lecture 34, because we are talking about PID controller design in a VMC buck converter. So, this lecture will talk about PID controller design, and there we found if we use a PID controller, we can actually by means of an analytical pole zero cancellation, stable pole zero cancellation, we can get fast order closed loop equation. But unfortunately, we could not get the suitable model matching up beyond like even up to 1/10 of the switching frequency. Our model was limited. So, here that is why we are considering this PID controller gain. We know the expression require a crossover frequency, this is the modulator gain, and this is the input voltage. So, we need to get the crossover frequency 1/20th of the switching frequency, because 1/20th means omega c will be 1/20th times 2 pi Fs, and Fs is nothing but 2 pi by 20 t, 1 by t is the time period. So, we are choosing 1/20th. Why? Because we have seen that this PID controller tuning for small signal, the model validity comes somewhat reasonably well below 1/20th or even less. So, we are choosing 1/20th switching frequency. Now, what is the modulator gain? Here we are considering the derivative of the output voltage, and in buck converter the derivative of the output voltage, if you take dV0 dt, it is nothing but capacitor current into C, and if you take C dV0 dt, then it will be IC, which is nothing but IL minus I0, where IL has a slope, which is rising slope of M1, because we are talking about step up transient, and this is particularly the trailing edge modulator, where we want to decide the turn on time based on our switching logic, or basically it will come from the closed loop system, but the off time will be decided from the type of modulator that you are using. For trailing edge, it is coming from the total time is constant. So, that means rising slope, the modulator gain here, since we are using a derivative action, it is injecting the inductor current information. So, even though you can use a separate RAM, that means if you have a sawtooth waveform, separate sawtooth waveform you can use, but this is like a control voltage, but this sawtooth we are taking a combination of the derivative of the output voltage, which is nothing but which carries the ripple information of the current as well as the sawtooth waveform. So, our combination of modulator gain will be 1 by M1 slope, that is the rising slope, plus the compensating damped into T. But since M1 we are taking a very small slope, and I will show our simulation case study, the M1 is very large. And what is M1 for a buck converter? It is M1 is nothing but V in minus V0 by L. So, if you substitute, Fm can be approximated by this, and if you write, the integral gain can be finally obtained pi 1 minus d by 10 L, where what is d? Because in buck converter you know V0 by V is equal to d. So, if you substitute, so this is our Ki that we are going to consider, and we will see simulation case study. Now, we have to find the proportional gain, and I told you the proportional gain needs to be found using large signal model, where you need to incorporate the ripple information, and that we are using phase plane geometry, and during this, when we carry out the phase plane analysis, we will not take the effect due to integral, because we told this effect primarily come near steady state. So, in large signal recovery, it is the proportional gain which shape the trajectory. So, we will ignore the effect, but it will create an offset, because it will ensure that steady state output voltage is regulated. Okay. So, now coming back to our time domain waveform in time optimal control, where the inductor current average was here, and you need to achieve the next average current here, and there is a ripple current, right. And you know, as long as the inductor current is smaller than the load current, your capacitor current is negative, and as a result the capacitor voltage will dip. But once it crosses, then your output voltage will, or capacitor voltage will slowly increase. Okay. And this is the corresponding phase plane diagram you can think of. Now, our loads transition step. So, we are starting from initial load current of I01. So, please remember, we are using I0 as an load current generic symbol, load current, which was I01 at the beginning of the transient, and at the end at steady state it will be I02, and that difference here we will find that this difference is delta I0, this is load step size, because it is coming from here. So, delta I0. Okay. So, at starting point it is starting from, and we are ignoring here the ripple effect, this ripple effect here, the starting point we are ignoring the ripple effect, so that we can take I01. So, this will not change very drastic transient response, because we are using a modulator. So, we may not get using the closed loop control perfect time optimal, but we will get close to time optimal. So, that is why this assumption is okay. Okay. Otherwise, you can incorporate this ripple parameter here, this particular chain, but it will simply increase the complexity of the derivation. So, you want to make the derivation simple, and it will be of course approximation, but that approximation is okay. So, we will see simulation case study. So, it will start from I01 and Vref this point, then on state trajectory it will follow this trajectory, and it will reach up to here. So, final value will be I1 V1. So, since you are plotting V0 versus IL, V1 I1. Next, it will follow the next trajectory, which is this off state trajectory, and for that this is my initial condition, and the final condition will be I02 is my load current, and also Vref is my reference voltage, I02 Vref. Now, for a synchronous buck converter, we can write the state space equation dx1 dt, where x1 is my inductor current and x2 is my output voltage. For ideal case, it is also the capacitor voltage. and we can also obtain dx2 dt. So, since we have derived this state space model multiple times, I am not going to derive, but if you write dx1 dt and dx2 dt, you can write in the state space form, and the states are inductor current and output voltage, and this q is the gate signal. So, when q equal to 1 for S on and it is 0 when S off, that we have discussed. High side low, it is high and low, and this is also given the derivation in this paper, you can get it detail. Next, the time optimal recovery, it starts with I01 load step that we have discussed. This is our I01, and then it goes to I02, the next value I02, and the difference is delta I0 step. So, now we can write dx2 dt divided by dx1 dt, and that will give you dx2 by dx1 here. Then you can write, and this next, this ZC is nothing but the characteristic impedance, square root of L by C. Next part, we have this equation and you need to solve it, and if you solve it will give the trajectory equation. So, the trajectory, the common solution is this, where q will determine, or here it is u, in this case u. So, here it is nothing but q equal to 1 or 0. So, the common solution of this trajectory can be solved by putting definite integral, and if you solve it, then you will get a generic form like this, where I, Vi are the initial vector, and If and Vf are the final vector. So, you can choose initial and final depending upon whether you are considering on state or off state, right. So, you can accordingly select this trajectory. So, that means if you solve this by putting the definite integral, so this is the equation, and if you rearrange, I am taking all the final quantity left side and the initial quantity right side, and that I am denoting as a function which consists of the final quantity and this function to the initial quantity. So, this I am defining, and you see from here you are getting initial quantity is equal to final quantity. Okay. Now, for on state trajectory, we have to substitute u equal to 1, right, and if you do that, this u equal to 1 this term. So, you can rewrite this equation, right. So, this equation we have already derived from the integration. Next, if we rewrite the equation for off state, we need to put simply u equal to 0. So, that means this term will get vanish and the input voltage is not there. So, you will get the off state trajectory. Then you have to substitute the instantaneous load current for I0, the final load current, that means the final load current which is the instantaneous value is I01 plus I0 delta I0, and if you substitute the final load current, so sorry, the initial instantaneous load current, because when you are talking about instantaneous means derivation, suddenly there is a load step. So, new load current is nothing but our I01 plus delta I0, and that is also my final current. So, in our expression, if you substitute, if you go back, so here you have this I0. So, this I0 is the instantaneous load current. Okay. So, this I0 is the instantaneous load current. So, this instantaneous load current we are putting I01 plus delta I0, and I02 it is the final current which is also I01 plus delta I0, but I01 is the initial current. If you substitute from that previous equation, you can find out I1 in the form of the final current into this V1 in this format. So, this you can check it out, because I am not going to derive all step, but this can be obtained from the earlier equation that we have written from this off and on state, because for off state I1 is the initial state and I02 is the final state, and V1 is the initial state and Vref is the final state. And if you go to on state, I01 is the initial state and Vref is the initial voltage. I1 is the final current and V1 is the final current. So, by that way if you will get two equation, two unknown, you can solve it I1, I1 V1 is the unknown. Now, at the switching surface where it will intersect, right, if you draw the switching surface, so at this point sigma, it is basically intersecting with the V1 and I1, and we are again approximating that we can, instead of sigma 1 we can take simply sigma. That is small approximation because we are ignoring that variation due to the ripple. Then sigma x I1 V1, if you substitute, again I told you I1 is the initial current and this is a new load current or the instantaneous load current, and this is my output voltage reference because that is there. Because what is our sigma? It was IL minus I0 plus Kp into V0 minus Vref. So, this I0 is nothing but our I01 plus delta I0. IL is the point where it intersects, it is I1. V0 is the point where it intersects V1 and Vref. So, then if you solve, you can get Kp because earlier we got I1 V1. So, that is known, everything is known except for Kp. So, you find out Kp and that will take this form. And you can do, so that means Kp can be, now this can be approximated to square root of 4 V in Vref, which is nothing but twice V in Vref. Since Vref is more or less constant for a voltage regulator, so we only need to compute the square root of V in. Another thing, the ZC square is generally that is our L by C, right. So, ZC square is nothing but L by C, and which again L and C are more or less known at the design stage, okay, and their variation is not very significant. So, you can compute online, only we need to know the load step size. Even if you do not know the exact value, fine, if you can know somewhat close, it is fine, but you can get some much better response than the linear control. But if you can perfectly, if you can estimate the load step or load current, right, or if you can sense in indirectly in case of LED driving and other application, then this is not a problem. So, the overall time optimal control, that gain, optimal gain will Kp, where this lambda will be equal to approximately equal to twice square root of V in Vref, but this is during step up transient. So, the method that we have followed to derive step up gain, you can do the same method for the step down and you will get everything else is same except the Vref will be replaced by. So, here you will find the Vref to be replaced by V in minus Vref. For 50% duty ratio, both are same, but for higher gain input voltage, high input voltage, the falling slope will be higher than the rising slope, and that is also already there in this paper. So, the using large signal. So, this is what we discuss about for current mode control. We know how to find Kp, we have discussed how to find Ki because Ki was coming from small signal model, and if it is a voltage mode control like a converter, then Kp is this. This is same that we have discussed, only some modification will be here, and Ki we have discussed the same Ki will be used, and Kd derivative is equal to C. And we have to, since we are using a derivative control, we need to use a band limited derivative, that is Kd into S plus tau d S plus 1, and this tau d to be much smaller than time period because we are using fixed frequency control. So, that tau d should be small, so that you can get close to derivative action because that will carry the ripple information. So, let us go to a simulation, say case study and check. So, I am first showing if we use a current mode control, suppose if you go back to our current mode control, and we all know about this structure, current mode control I have discussed multiple times, but here we are taking load current feed forward. And here this feed forward gain I am setting from internally, either if you set 1 for buck or if you set 0, there will be no load current feed forward. And here we are setting the gain from our MATLAB code. So, we can use simply proportional gain, even you can use a PI controller, because in our tuning parameter we have to choose this PI controller. Okay. Now, if we go back current mode control using large signal based PI controller. So, this derivation, I think this should be a different derivation. So, now we want to run this buck converter using current mode control PI controller, and if we run it, we are giving all the values from here, because I will discuss in detail. This is under current mode control, where it undergoes a 20 ampere load step from 1 ampere to 20 ampere, and you can see it is almost like a close to a time optimal, where output voltage is not exactly time optimal, because there are some effect, but it is much faster. Now, if we go for voltage mode control, so if we disable this, on top of that, if we comment it, and if we go for voltage mode control design, again it is a large signal with design, and we will discuss this in the subsequent lecture. And if we change the color, blue color for voltage mode, and you see it is taking the voltage mode control logic, that means buck converter voltage mode control logic, which is nothing but simply this converter voltage mode control, no load current, nothing. If you go back, it has a ramp with a very low magnitude I am using, and this is a error voltage, and this is where is a compensator. So, if you run it and you are using a very small ramp, and that ramp is almost maybe very low value of ramp we are using. So, if you go to voltage mode control, you will find the response is close to optimal solution. Okay. And if you go to the current response, it is also close to optimal solution. So, that means we can get time optimal recovery for both current mode and voltage mode control. So, with this I want to summarize the recapitulation of PID controller tuning objective, then large signal modeling of a buck converter, derivation of the tuning rule in a buck converter, and that we did for current mode as well as voltage mode control, and the summary of tuning parameters. So, with this I want to finish it here. Thank you very much.